In this video, we're going to talk about compound interest. Interest refers to the cost of borrowing money or the money earned from an investment. Often, the value of an investment increases over time. So an investment that's worth $50 today might be worth $52 next year. That extra $2 is interest. So suppose Simon deposits $500 in a bank account that appreciates at a rate of 4% per year. Let's determine the amount that'll be in Simon's account at the end of 1 year, 2 years, and 3 years. Well, first we're going to do it. We're going to do this question in such a way that it helps us to establish the formula that we're going to use for other questions. So we see at the end of 1 year, Simon will have 104% of what he started with because he's gaining 4% per year. So 500 times 104%, in other words, 500 times 1.04 is 520. At the end of 2 years, Simon will have 104% of what he had at the end of 1 year. So we'll take this 500 times 1.04 and we'll multiply it by 1.04. In other words, 500 times 1.04 squared, and that'll equal 540.80, $540.80. At the end of 3 years, we'll take the amount of 500 times 1.04 squared and we'll multiply it by 1.04 because, again, Simon's money is increasing by 4% per year. So that's like saying 500 times 1.04 quantity cubed, which is roughly equal to $562.43. So what we're establishing there is a formula. When we're talking about an annual rate of growth, we can say that A will equal P times 1 plus I to the n. A will refer to the final amount of the investment. Sometimes that's called the future value. P will refer to the initial amount invested, and sometimes that's called the principal or the present value. And I will refer to the annual rate of growth expressed as a decimal. For example, 4% will be expressed as 0.04. N will refer to the number of years. Now, we're going to get into an issue later called compounding frequency. We'll talk about that in a few minutes, but we just need to realize that this annual rate of growth, for what we're talking about here, we're assuming that we're compounding it annually. Now, we'll get into what that means shortly, but we've established a formula for compounding annually. But like it says here on this next slide, however, interest is not always calculated annually. For example, sometimes we calculate interest semi-annually, twice a year, or quarterly, 4 times a year, or monthly, 12 times a year, or weekly, 52 times a year, or daily, 365 times a year. So for example, if we were calculating interest quarterly, 4 times per year, then what we would do is, instead of saying that the person is getting 4% once each year, we would say that the person is getting 1% interest 4 times per year. At first glance, it sounds about the same. It's a little bit different. And so if we're calculating interest quarterly, which means 4 times per year, what we do is we divide the annual interest rate by 4, but then we calculate the interest 4 times more often. And this is referred to as the rate of compounding. So, and then finally, something that you often see is this symbol here. If we're talking about an annual interest rate of 4%, then we say 4% slash A. It's Latin for per annum. Per annum. That's what this slash A means, which means per year. So what we would do if Simon wasn't getting 4% per annum compounded quarterly, what he would really be getting is 1% interest 4 times more often. So if we were to do that, we would, instead of saying 104% or 1.04, we'd say 101% or 1.01, but then instead of only raising it to the exponent of 3, we'd raise it to the exponent of 12. If we did that, we would see that Simon got $563.41 approximately. So notice that after 3 years, if we compound annually, Simon's amount in the bank account will be $562.43. But if we compound quarterly at the same rate of interest, we end up with $563.41. So in other words, compounding frequency has an impact on the final amount of an investment along with the interest rate. Differences become greater over time, the differences between them, because we're dealing with exponential functions. So now, in summary, a formula that can be used for the compound interest questions is A equals P times 1 plus I to the n, where A is the final amount or the future value, P is the principal or the present value. The values of I and n can be determined using the table shown. And remember, the annual interest rate has to be expressed as a decimal. So if we are talking about an annual compounding frequency, then I will simply be equal to the annual interest rate and n will be equal to the number of years. But if we're talking about a semi-annual compounding frequency, then what we need to do is divide that interest rate by 2, but calculate the interest twice as often, so we'll double the exponent. If we're talking about a quarterly compounding frequency, we divide the annual interest rate by 4, but multiply the number of years by 4 to give us our exponent. And we follow a similar pattern here with monthly, weekly, and daily. Every time we have a certain compounding frequency, whatever we divide the annual interest rate by to get the value for I is the same amount that we multiply the number of years by to get the value for n, or the exponent. Now notice the value of n will always be equal to the number of compounding periods. So for example, when compounding monthly, n will refer to the number of months. So let's imagine Yolanda invests $3,000 in an account that appreciates at a rate of 5.4% per annum compounded semi-annually. We'll determine the future value of the investment in 7 years and determine how much of the future value is interest. So P is the principal invested, A is unknown. I, since it's a 5.4% interest rate annually, we'll say I to begin with is 0.054, but now since we're compounding semi-annually, we divide that by 2. And that might seem unfair, but then remember, we're going to take that exponent, and instead of just using the number of years, we're going to multiply it by 2. And so that's going to more than make up to Yolanda for the dividing by 2 with the I value. So A is P times 1 plus I to the n. In other words, A is 3,000 times 1.027 to the exponent of 14, which is equal to roughly $4,356.20. So we see the future value of the investment is approximately $4,356.20. If we wanted to know how much of that was interest, it's simple. Just take that future value and subtract the principal. And whatever the difference is, that's interest earned. So in this case, she's earned roughly $1,356.20 by just letting the money sit in the bank. Now imagine Filippo invested a certain amount in a bank 8 years ago at a rate of 3.6% per annum compounded quarterly, and today we see that the investment is worth $1,065.63. We'd like to know the amount of the original investment. So what we do is we say, well, our final amount is $1,065.23, but we don't know the principal invested. Now, the annual interest rate is 3.6%, so it's 0.036, but we need to divide by 4 to get our I value, and then we need to determine the number of years, which is 8, and multiply that by 4 to get our n value. And so now we can say A is P times 1 plus I to the n. We can divide both sides by 1 plus I to the n and get A over 1 plus I to the exponent n equals P. And remember, if you have a factor of the denominator with a positive exponent, that can be with the same base, put it in the numerator, make the exponent negative. So we get a formula for principal in questions like this, which is A times 1 plus I quantity to the exponent negative n. And so we can say that the principal will be $1,065.23 times 1.009 quantity to the exponent negative 32, which is roughly 800 bucks. Now imagine we wanted to know the annual interest rate compounded monthly that would cause an initial investment of $400 to increase to $508.38 over the course of 10 years. Well, we see in this case that our final amount, our future value, is 508.38. Our initial amount, our principal, is $400, and I is unknown. N was equal to 10 times 12 because it's 10 years and we're compounding monthly. So 10 times 12 is 120. So we can use our formula here. And when we do that, we want to isolate I. The first thing we're going to do is divide both sides by 400, which we've shown here. Now we have 1 plus I quantity to the exponent 120 isolated. What we can do is either raise our value of 508.38 over 400 to the exponent 1 over 120, or if our calculator has the button that gives us the 120th root, we can use that. And when we do that, we end up seeing that 1 plus I is roughly equal to 1.00200, which means I is roughly equal to 0.00200. Now, if you go back a few slides, there was a slide that said that in the case of a monthly interest rate, I would be equal to the annual interest rate divided by 12. So if I is equal to 0.00200 and we want to know the annual interest rate, what we're going to have to do is multiply both sides by 12. So since that's what it says here, since I is equal to the annual interest rate divided by 12, therefore I times 12 will be the annual interest rate. The annual interest rate will be roughly 0.0240. Now remember what that means. You have to be able to work backwards a little bit here. You know that if the annual interest rate was 2.4%, that we'd be able to represent that as 0.024. Well, we want you to be able to say, if we know that it's being represented as 0.024, we want you to be able to say the annual interest rate is 2.4%. Okay? Now, suppose on the day that his son was born, Robin invested $1,000 into an account that paid interest at a rate of 4.4% per annum compounded quarterly. On his son's 6th birthday, Robin invested an additional $600 into the same account. If there were no further deposits or withdrawals and there was no change in interest rate or compounding frequency, we want to know how much money will be in the son's account on the 18th birthday. Well, I like to think of this as a multi-phase question. Anytime there's a new deposit or a new withdrawal or a change in interest rate or compounding frequency, we need to start a new phase. So phase 1 lasts from Robin's son's birth to the 6th birthday, which is 6 years. So phase 1 is 6 years. Phase 2 lasts from the 6th birthday to the 18th birthday, which is 12 years. All right, so in phase 1, we don't know the final amount. In phase 1, remember, the final amount will refer to the amount in the son's bank account on his 6th birthday. But we know the principal was 1,000. We know our interest rate was 0.044. We're going to divide that by 4 because it's quarterly. And we're going to multiply the number of years, which is just 6 times 4 to get 24. And we're going to use our fairly simple formula to determine that when the son woke up on his 6th birthday, there were $1,300.25 in the bank. Now, whatever the son ended phase 1 with is the same amount the son began phase 2 with, because it happened on the same day. So the son wakes up on the 6th birthday, phase 1 is over, son moves into phase 2 with $1,325 in the bank. $1,300.25 in the bank. Now, what happens in the next phase, there's actually an error on the screen here, so I'm going to correct it for you. What happens in this next phase is we need to add $600. So there's a little mistake on the screen, but I'm fixing it as we go. See, Robin invested an additional $600 into the same account. So we have to say that the principal is equal to $1,300.25 plus 600. The son woke up with this much money in the bank. The dad deposited $600. The son now has $1,900.25 in the bank account. That's what P equals, $1,900 $1,004.25. Okay, now the rest of what's written on your screen is correct. I is equal to 0.044 divided by 4, which is 0.011, and n is equal to 12 times 4, which is 48. Now, since the second phase lasts for 12 years, we're going to use the formula given. But instead of letting the P, the one mistake here is instead of saying that P is equal to $1,300.25, we'll say it's equal to $1,900.25. And we're going to take that much money and we're going to multiply it by 1.011 to the exponent 48. So I'm doing that right now as we're waiting, and the amount is roughly $3,212.67. So there will be roughly $3,212.67 in the son's bank account on his 18th birthday. Now, suppose Georgette deposited a sum of money in an account that paid 3.8% per annum compounded semi-annually on the day that her daughter was born. And on her daughter's 10th birthday, she deposited an additional $800 in the same account. And finally, on her daughter's 16th birthday, there were $3,742.18 in the account. We'd like to know how much Georgette's initial deposit was. So what we're going to do is do a phase one, phase two analysis, but we're going to do it backwards. So this is a multi-phase question. Recall that anytime there's a new withdrawal or new deposit or a new interest rate or a new compounding frequency, we need to make a new phase. So in this case, phase one lasted from Georgette's daughter's birth to her 10th birthday, which is 10 years. Phase two lasted from the 10th birthday to the 16th birthday, which is 6 years. Now, like I said, this question is different than the last one because it's a backwards two-phase question. So we'll go to the end of phase two. Phase two lasted for 6 years. The daughter ended phase two with $3,742.18, but we don't know what she began it with. We know that the interest rate was 0.038 divided by 2, which is 0.019. And we know that n will be 6 times 2, which is 12. So we know that the principal, the amount that the daughter began phase two with, will be given by this formula which we established earlier. So $3,742.18 times 1.019 to the exponent negative 12 equals roughly $2,985.62. That means the daughter began phase two with $2,985.62. Okay, that's interesting. But now remember, she had just had $800 deposited in the bank. So what we're going to do is we're going to subtract that $800 that the daughter got on her 10th birthday, the beginning of phase two. We're going to subtract that, and then this amount here, the $2,185.62, that'll represent what she actually ended phase one with. So at the end of phase one, there were $2,168.62 in the bank. That now becomes our A value because we're trying to find the principal, i.e. the amount invested on the day the child was born. So the principal is unknown. The I value is 0.038 divided by 2, which is 0.019. The N value is 10 times 2, which is 20. The principal is A times 1 plus I to the negative N. And when you plug these numbers in, that's roughly equal to $1,500. What that means is that the initial amount was $1,500. And if you think about this backwards, it actually kind of makes sense. The mom deposited $1,500 the day her daughter was born. It grew to $2,185.62. She then added another $800, which got her to $2,985.62. She then, going back one slide, she took that $2,985.62, left it in the bank for 6 years, and ended with $3,742.18. So a question like that's a little more complicated when you have to work backwards. Now let's try this question. Max purchases a brand new necklace. He makes a down payment of $800 and finances the rest at a rate of 12% per annum compounded monthly. 18 months later, he makes one payment of $598.07. He'd like to know what was the purchase price of that necklace. So the purchase price is equal to the down payment plus the present value of the financed portion. Okay? So there's two components here. The down payment. So the price is at least 800 because Max put 800 down. That goes into the price. But we also have to figure out what's the present value of this 598.07. That 598.07 is the end amount. It's like the A, or what we call the future value. But we'd like to know what was the P, the principal or the present value of that. So we say A is 598.07 and P is unknown. We know that I is 0.012 divided by 12, which is 0.01. N is equal to 18. When we're compounding monthly, N is equal to the number of months. If it helps you to think about it, if you're stuck on formulas, 18 months is 1.5 years. 1.5 times 12 is 18. So we can determine N is 18 either because there are 18 months and we're compounding monthly, or like I just said, because 18 months is equal to 1.5 years, so N is equal to that. Either way you determine N is fine. So we can then say the present value of the financed portion is 598 times 1.01 to the exponent negative 18, which is $500. Since the down payment was $800, therefore the purchase price was $1,300. Now, it might help to just think about this for a second. So now that we're done, let's think about what this is saying. Max sees a necklace. There's my drawing of the necklace. And on the necklace is a price tag of $1,300. Max says, you know what, I don't have $1,300, so I'll give $800. Well, Max now owes $500. So Max is allowed to take the necklace home, but has to pay interest. So what he does is he 1.5 years later gives them $598.07. Now, obviously, 1.5 years later, they're going to want more than just the 500 that was owed because money grows over time. They're going to want, and it's the cost of doing business. Max is going to have to give them more. So Max actually has to give 598.07 to make up for the 500 that he owed a year and a half ago. So that's how one of these questions works, okay?